DPUs have definitely showed their value in the marketplace. What we have seen that they can perform networking, storage, and security better than some of the traditional CPUs, both on a performance and performance per watt as such, as well as performance per dollar basis, right? What started, DPU started with the top tier clouds, but now are part of the 5G business as well. And you'll also see them migrating to the server, networking OEMs, tier two clouds, and others. Primarily at a top level, I would see the DPU market can be classified into three. Telecom is the most interesting at this moment. It's growing because of the need to build the 5G infrastructure with better power performance. We do have the Octeon series from Marvell, which deliver better price performance than FPGAs or x86 chips. And we see that adoption is continuing to climb. The second category there, I would say, is the cloud DPUs. That's the attractive market where most have their own customized design. And we have worked with some of them to include our chips there, but we cannot provide names there. And to continue on that, the cloud, one more use case within the cloud is for the dedicated security devices, which are gaining momentum. We have a liquid security PCIe card for clouds, which essentially perform the encryption and key management. Currently, million set of keys, and there are 100,000 operations a second with a fraction of the energy and the hardware and accordingly the rack space that's needed there. All this is possible because of the optimized DPU inside it, right? And then on top of that, the third market that's coming in is the enterprise, where we'll look at having Octeons as part of the firewalls and as part of the OEM equipment as well. So overall, DPU is growing significantly in the marketplace beyond the traditional cloud or 5G into the other domains as well. If you look at DPU, they are a combination of general purpose processors and then specialized accelerators added to it, right? Now, most of the legacy applications are typically written for general purpose processors using the traditional x86 architecture or others, right? And then the challenge used to be that how do we adapt the code base that was there on those architecture or platform and to leverage it on the specialized hardware acceleration capabilities of the DPUs, right? It needed the engineers to have the advanced knowledge in specific areas because you might have a crypto engine, you might have the compression algorithm, and all of that knowledge was required to build your software and other applications on top of it. What has happened in the industry and in the common strategy is that there has been an evolvement of open source community, which is supported by software libraries. And you will hear these terms called as DPDK, SPDK, where we make it easy for engineers to write applications for DPU and then make it available on these libraries, right? And then the DPU vendors, they ensure that the specialized accelerator functions have those open source software libraries and pick up from there and then build further from there. So that's been a good evolvement that has happened recently and is solving those legacy challenges that we saw in the past. Very true. For sure, turnaround time, or I would say on time for the market. But it's not just that. The overall cost to develop DPU is significantly high because they are in the latest and greatest or most advanced node, right? And then that's where it is very, very important for all the DPU designers and manufacturers to how do we do things right the first time, so that right we can have a working silicon and the overall system be ready for the market with the differentiation that we are talking about. Now, being on time with quality is being addressed by many things. And in a typical chip design world, what we do is that a lot of design activities are having a shift left, where you push things early in the game, where you try to do a co-design to start with, and then go start doing things in the architecture or in the early design phase or exploration space, and then try to evolve lot of main architecture decisions early, and then have a smooth implementation and sign off for the manufacturing test phase, right? It's a part of what we call as a continuous development to shift left, to do things right the first time, and then make DPUs available on time with quality and with the controlled cost that it will incur being in the advanced technology now. For sure, first thing I would say is that they reduce energy consumption, right? And as they do it, because the waste heat that is coming from this energy consumption, the rack space, because less heat mean you can put more hardware into a single rack, the processing time, and finally, ultimately, the cost with these specialized accelerators that we are building. What we see the world is discovering now is the limitations of general purpose processors. Clouds and other customers will ultimately move to architectures which is around a portfolio of what we call as the specialized processors, and DPU is a great example for that. CPU will remain to be part of the mix, but their role will be lessened, and then we'll have those DPUs involved part of it. Another example, if we pick up in AI, we will see that AI models will continue to grow in complexity and almost at 10x per year, if not less. And that's unsustainable without a specialized processing, which again asks for a need for a DPU. Finally, in the end, right, what we call as that you want to consume less energy, have small boxes that can fit into tight spaces, and require a very limited human intervention. And that's what would be the norm that we'll need. And DPU will be the part of the equation to realize that goal.